Okay, so we want to look into a half-life question. It does have two parts. So we're going to start by looking at how much of this is left after 4 years, and then we're going to move into the half-life of it. So you get double practice here. I always think it's a good idea to write down as much of the information and kind of like organize your information. And so we have a formula, right? We have A of t is going to be 500 e to the negative 0.032 t. Notice this negative here, right, is confirmation that we're talking about a decay function, right? It's decreasing over time, okay? Hopefully you can see where all the pieces of this function come from. There's the 500 right here, right? This 210 and this 210, they're both names of elements. So they're, I don't want to say misleading, but they're not relevant to what we're talking about, right? There is one other piece of information that's maybe not explicitly given, but it is there because of what we have in the formula. So this 500 grams, we said, that's our initial amount, right? What is this 0.032 value? Well, that's your value for K, right? 0.032, which if you want it in its percentage, you move it over 2 spaces, 3.2%. The decimal is just fine. You don't have to turn it back. This is really useful to us, right? So I do want to look at our two pieces of our question here. One, can we find the amount of radioactive lead that's still there after 4 years? And then two, can we find its half-life? Now, because we're decreasing, we should find that the sample shrinks, right? It should be smaller than 500. If it's growth, it should be larger than 500. So first part of this question is, can you find after 4 years, now we didn't get a starting year, but that's fine. I'm just looking at this when t is equal to 4. So A of 4 equal to 500 e to the negative 0.032 times 4. Again, there's a lot of simplifying that goes into this question, so just be very, very careful. Don't drop your decimals or anything like that. So your first part is 0.032 times 4. So this portion right here is 0.128. So we've got A of 4 is 500 e to the negative 0.128. Excuse me. I should put a negative here. So we say e to that power. And again, this is going to be a lengthy decimal. So you can write fewer decimal places down, but keep them all on your calculator so you don't get it wrong. This is going to be 0.87985. So we're looking at A of 4 is 500 times that 0.87985. It makes sense that we get a value smaller than 1 because we had a negative exponent, right? That makes it a fraction smaller than 1. There, it takes a reciprocal. And then we want that times 500. A of 4 is going to be 439.92668. Okay. If we round that, we can say that after 4 years, there's 400, let's go with 439.9. I believe this was measured in grams. Yes, in grams right here of radioactive lead-210. So grams of radioactive lead-210, okay? So that's the first part that this question was asking you about. It is a decay question, right? The second thing this question was asking you to find is, what's the half-life? How many years will it take for there to be, how many years will it take for there to only be half of what we started with, right? Now, you could approach this two ways, right? What I would maybe consider a lengthier approach, it's purple, but I would consider this as maybe a lengthier approach. You could say, what's half of that 500? slightly lengthier, right? 250, and you can plug that in for A of t. So you would have 250. So you would have 250 is 500 e to the negative 0.032 capital T, right? So you could do that. You could take that approach, negative 0.032 capital T. So you can take that approach, but just as, maybe a little easier, you can use the formula ln2 is equal to kt. And that way we don't have to deal with all the division and kind of the extra stuff, right? For this formula, the only other thing we need is the value of k, and k is going to be 0.032. Notice the value of k is not negative on its own. The reason why it's negative in the first part of this question in our formula up here is because it's a decay value. So the negative kind of comes with this original function formula. It does not follow us, if you remember how we got to this formula, right? The negative canceled out with the negative exponent on the ln over here. So we do not need a negative here for k. Okay, hopefully that makes sense. So I just plug that in. I want ln2 equal to 0.032 capital T. Divide both sides. Throw it on a calculator. And you end up with T is approximately 21.660849. This is measured in years. I'm going to round it again. I'm going to take 2 decimal places. We've been taking 1 decimal place. So its half-life is approximately 21.7 years, right? So you can see that after 4 years, I mean, it decayed, but not drastically. We started with 500. But as we move into its half-life, it would take 21, almost 22 years for it to actually get to that halfway mark. Okay, I will see you in the examples on the next page.